way that we can use this identity matrix is to work with A and A with -1 on its shoulder, so A inverse, because the inverse matrix times the square matrix A is equal to the identity matrix. Now you see right here, we have, there we go. So we have A, we don't have A inverse. How can we find that inverse matrix? Well, we'll be able to do that in a couple of slides. Right now, we're not really equipped to do that. It's a mystery for us. All right, what you need to realize at this point in time is that as we work with A and A inverse, when you multiply them together, you get the identity matrix. All right, so we'll talk about how to figure this out here in a couple of slides. That's just an interesting mystery. Think about it because that's coming up. All right, and it's a challenge. So right now we start us out with something easy. Are A and B inverse matrices? Are they? Well, let's see here. So A times B. So we have -4 times 2 plus 3 times 3, because we're taking row, column. All right, then we have -4 times 3 plus 3 times 4. Right, so row and column. Now we come over here. So we have 3 times 2 plus -2 times 3, row times column. And then we have row times column right here. So 3 times 3 plus -2 times 4. All right, so -8 plus 9 is 1. -12 plus 12 is 0. 6 minus 6 is 0. And 9 minus 8 is 1. So A times B, right, equals that identity matrix right there. That's nice. And what about B times A? B times A also equal this identity matrix as well. So let's call it I. Trying to write an M right here. It's not coming out very well. So A times B equals I. So what about B times A? See what happens with that. So 2 times -4 plus 3 times 3. Then we have 2 times 3 plus 3 times -2. And then we come over here, so 3 and 4. So 3 times -4 plus 4 times 3. Then we have 3 times 3 plus 4 times -2. -8 plus 9. -12 plus 12. 9 minus 8. 6 minus 6. So what do we end up here? We end up with 1, 0, 0, and 1. So A times B is equal to B times A, which is equal to I. Are these inverse matrices? Yes, they are. What about this one right here? Oh, let me go ahead and clear the ink from the page. Clear. So AB. So we have row 1 in A times column 1 in B. So 6 times 1 plus 2 times -2. Row 1 times column 2. So 6 times -2 plus 2 times 6. Now we have row 2 in A. So 2 times 1 plus 1 times -2. And we have row 2 in A times column 2 in B. So 1 times 6. So what do we end up with here? So we end up with 6 minus 4. Ooh, guys. 6 minus 4 is 2. -12 plus 12 is 0. See here, 2 minus 2 is 0. And 6 minus 4. Oh, guys. Well, that is absolutely not true right here, because we need 1, 0, and 0, 1. So AB is out, right? Because A times B, phase of 2 by 2, needs to be equal to I sub n, or I sub 2. So and that's out. So what about BA? What about BA? Let's take the first row in B. So 1 and negative 2. And the second row in B is negative 2, 6. Negative 2, 6. And let's take that times the first column in A. So 6 and 2. So 6, 2, 2, and 1. All right. So we have 6 minus 4, 2. 2 plus negative 2 is 0. Negative 12 and 12 is 0. Negative 4 plus 6 is 2. So AB is equal to BA, but those are not equal to the identity matrix. So this first set is a yes. The second set is not a chance, guys. Sorry about that. All right. What about this right here? If M has an inverse, then it is said to be invertible or non-singular. So they ask us right here to find our inverse if it exists. If it exists. Okay, so we have a little bit of a problem right here. So the row with zeros on the left indicates that our matrix M has no inverse right here. Ooh. Has no inverse. Well, that's a shame. All right. So during the process of finding the inverse of M, that's a shame, because what's going to happen is that if we find a row that gives us all zeros to the left of the vertical bar, so right here, we get something like that, then M has no inverse. So in this case, M, since it has no inverse, M is a singular matrix. M is a singular matrix. All right. We're getting some more information here. Look at this. Given the matrix A is equal to, so it's a 2 by 2, so they're calling this row 1 A and B, row 2 is C and D, then they tell us that our inverse is given by this. So A inverse is equal to, look at this, guys, 1 over AD minus BC times, and look what they did here. They took A and D, they switched their locations, and they made B and C negative. Huh. See what that means when we get a practical example to work with. So here's another way of stating it right here. So if we let A equal this 2 by 2 matrix, then A is invertible if AD minus BC is not equal to 0. It is not invertible if AD minus BC equals 0. All right, now this quantity AD minus BC, we call that the determinant of A. We write that DTA equals AD minus BC. All right, so this theorem, the inverse of the 2 by 2 matrix, tells us that if and only if the determinant is not equal to 0, then A is invertible. So it's invertible or non-singular. Right, so invertible, non-singular, if AD minus BC equals 0, then it's not invertible and it's singular. All right, then we move into how to calculate the determinant of a 3 by 3 matrix. Before we do that, real quick, guys, let's just head back to this and let's see if we can figure out what our inverse matrix is. Well, what's that going to be? Because right here we say that the inverse matrix is given by 1 over, so AD minus BC. So AD, so 0 times 2 minus B times C minus 4 times 1. And that's equal to, okay, so we switch the 0 and the 2, and we make the 1 negative and 4 negative. Okay, so did I do that right? Let's see. 2, 0. Okay, so 2 and 0 switch, and this should be a negative 4. That should be a negative 1. There we go. All right, so we have 0 minus 4. So negative 1/4 times this matrix. Guys, that's scalar multiplication. So negative 1/4 times 0 is 0. Negative times negative is positive. 4 times 1/4 is 1. Negative times negative is positive. So multiplicative identity right there, anything times 1 is that thing. And then negative 1/4 times 2 is negative 1/2. So that, guys, is our inverse matrix.